Okay, yeah. Hello everyone. This is another session of Designing Data Intensive Application Book Club. And today we are going to start with a new chapter, which is Trouble with the Distributed Systems. Okay, so up till now we have discussed various things in distributed systems. We have discussed replication, partitioning, we have discussed transactions, and in a lot of those chapters we have discussed what will be the scenarios if something fails in these distributed systems. But in this chapter we are going to discuss more things that are going to fail. The author says that the previous chapter has been too optimistic, that we have still not considered all the possibilities about things that could fail in a distributed system. So here in this chapter we are going to see those more things which can fail in distributed system, and then in future chapters we will see how these failures could be handled, these kind of problems or faults could be handled, and then we could make overall more reliable distributed systems. Okay, so so to start with, so thinking about single machines, the difference between single machines and the distributed machines is that uh, in single machines, they have been designed by hardware manufacturers in such a way that either they will completely fail or they will succeed. Like they have not been designed in such a way that they will show you some like they will show you a partial result which is incorrect or something, right? Unless you have introduced a bug, a single machine will itself not introduce a bug, right? So uh so but the same thing, it is not true for the distributed systems. In distributed system, the model with which computer has been designed, the idealized model, that does not hold in a distributed system. In distributed systems we can have these situations where we are in the situation of partial failures, or where we are in a non-deterministic state where we don't know whether the thing has completely failed or not. And we are going to discuss what these non-deterministic states are. But so overall, like we can now building these distributed systems, now we can no longer work under the assumptions of single system that hey, either the thing will completely fail or it will succeed. There could be these non-deterministic situations, and we have to make sure that we have taken those into considerations and our overall system can handle those situations, right? um, so the one example in single machine failures is that either like you will see a blue screen of death, or either you will see that your system is not working at all, but you will never see a situation where like you have written some code on a single machine, right, and it is giving you incorrect result. Imagine that situation, that on a single machine you have written some code and it is giving you some incorrect result, and but it's not your bug, like you have written everything correct from your end, right? That never happens on a single system. So okay, so that was one thing, that these distributed systems, like they are unreliable in such a way that they have this non-deterministic states, right? uh, Not only that, the other thing, so in this section, expectations from cloud computing, uh, so one thing is these systems are non-deterministic, but not only that, from these cloud computing systems we want to achieve some of the more advantages that a single machine does not have. And those, some of those advantages are that a system, we want these cloud computing systems should be always available and online, right? So what we mean to say here is that a single machine, it like it has some chances of failure, right? And if it is failing, then your system is unavailable. But from cloud computing, you never want those situations. You want your system to be always online and always available, right? The second thing is that so basically these hardware devices, you can make them more reliable. Like there is a limit to which you can make them more reliable, but also like if you make those systems more reliable, the manufacturing cost increases. And uh, but in these cloud computing scenarios, you also have to think about the cost. So basically, your overall system is made up of commodity hardware, and that commodity hardware is not very expensive hardware, and it is more unreliable. So right, so what we're saying is that we want to build a system from like commodity hardware, not some special hardware which has been designed that it will be more reliable than this commodity hardware to reduce the cost. uh, then the other thing which is expected is that since now we are going to have large number of machines, these commodity hardware, so the probability or the possibility of some nodes failing is also more, right? Because you have more number of machines. uh, okay. And the another important aspect is that so this ability for this your system to tolerate faults, it's not only for the scenarios where something will fail, uh, n- which is not under your control. Even in situations you might want to bring down a node and then work with your system. And the example is when you're doing rolling upgrades and all, then you intentionally bring one of those machines down, you update it, and then bring that machine back, right? So in these scenarios there are those intentional moments also where you are bringing the system down, right? uh, and also the last expectation is that in this multi-center environment, your calls are going over the internet, which can have much more higher latency. Whereas if you're considering a situation of single computer and a single machine, like everything is happening on on that one machine, right? And so those network calls and delays are very low. Whereas here you have to work under the assumptions that those network calls might take much more latency because they're going over the internet and they might be going across the region, right? So so overall, we have to build this system which is more reliable, and it is made up of components which are individually unreliable, right? So I was thinking of this example. So let's say you buy a hardware which has, let's say, zero point 0.1 zero point 0.1 probability of failure and zero point 0.9 probability that it will be reliable, it will not fail, right? And whereas you buy another commodity hardware which has zero point 0.7 probability of being reliable and zero point 0.3 like higher probability of being failing, right? So now what we are saying is that we have to build overall reliable system from this commodity hardware which has zero point 0.3 probability of failing, right? So basically think of this case of replication, that if you have these three nodes which have zero point 0.3 reliability, the probability that your data is lost will be when all the three nodes fail, and the probability of that happening is zero point 0.3 into zero point 0.3 into zero point 0.3, right? Which is lesser, which is 0.027, which is lesser than a single machine. If you would be storing the data in a single machine, which although that single machine was more reliable, it was zero point 0.9 probability that it will be not failing. But still, you have made a overall distributed system more reliable than that individual hardware, which was more expensive as well, right? So, okay, anyone want to add something here? Okay, so moving on to what is unreliable. Yeah, so okay, so the first thing which is unreliable in these distributed environments is unreliable network, right? So basically, all this cloud computing environment, they're made of shared nothing architecture. What is the meaning of shared nothing architecture is that each machine has its own CPU, memory, and hard disk, and they don't share anything, right? They don't have that shared network disk or something. Each machine has their own disk, and they're talking to each other over a network, right? So they have this shared nothing architecture, and they use this internet to send asynchronous packets of information, right? And so with asynchronous network, what we're saying is that when a when a node sends a packet, there is no guarantee that the packet will arrive. And why there is no guarantee that the packet will arrive is because of this diagram, that when you send up a packet, it can fail at various stages. So, so looking at this diagram, if you see that when the client sends and make a network call to this service, either it could fail in the network when it reaches the network. During that time it could fail, or it could fail when it reaches the service because the node which was serving your service, that has failed. Or another thing that could happen is that your service was working fine, it responded successfully, but again when it was being responded back to you over the network, then it failed, right? So there are various stages at which the things can fail. And so when you are sending the request, you don't know whether it has succeeded or not. And probably on the service side, the call has actually succeeded and you might have not got the response. So you have to handle those situations. Like, for example, let's say your service was sending an email, right? And in this scenario, your service has received your message and it is going to send that email to your friend. But if you look at this, you might see that I have not got a response back, so I will retry. In that case, you might send like two duplicate email, right? So yeah, so basically this situation where the client is sending a message and it waits for the response uh, to see whether his call was successfully made or not. This process is unreliable in a way that uh, your call could have succeeded or failed, you don't know. And waiting for the response, you don't know if the response will arrive, how long it will take for the response to arrive, and if the thing actually succeeded or failed, right? So the the approach that you could follow in this scenario is that you could have a timeout on the client. So basically the client can say that I will wait for this much amount of time, and if I don't hear back in this much amount of time, I can say that my request was not successful, and then I will do something about it. I will either retry. If I have to retry, probably I will do a idempotent retry so that I don't repeat the sending same message again. But those could be some other strategies that you could apply. But the first thing you need to know is whether your request was successfully served or not. So for that, you need to wait for response, and the response could take much more time than expected. So you have to set those timeouts, right? Uh, okay. So uh, one of the thing that was mentioned is that, and these network faults where these things fails, these are very common. Like they had given some examples in the book that like there are a lot of situations where these network calls could fail. And even if this network calls are like not quite often, even if they are rare, like even if you're within the data center and you're saying that they won't happen more often, still you have to, still even if if there is a slight chance, you have to build your system to and take in account of that situation, right? So 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 now we have to detect these faults. So faults means that your service or your network something is not responding. So why, like to give those concrete examples, why do you need to detect these faults? So one of the example is, let's say if you have a load balancer, right, and your load balancer is distributing the node across your application nodes, then you need to know like which nodes are working and which nodes are in the failure state, because you don't want to send the client request to the nodes which are down, right, which are not responding. And so that is one example where you would need to know that there is some fault in the system. The other scenario is that if the leader fails, right, then one of the followers has to be made the leader. So we have seen in these previous examples, so somehow that leader should know that uh, not leaders, somehow the overall system should know that the leader has failed, so that they can start the re-election, right? So how do we know that something has failed? How will the load balancer know that one of the node has failed, or how will the overall leader follower system will know that its leader has failed? So in some situations there are ways where your system can actually tell you something has failed, and you can get those feedbacks. And those situations are, so like one of the situation is when you reach your machine, right, which is running your process, which is serving your request, and that process is running on some port, right? So if your request is reaches that machine, and then the machine sees that there is no process running on the destination port, then the OS will send you this reset or fin package in reply. So with that reply, if you are seeing that you're getting this kind of reply, then you know that the process is no longer running, and the process no longer running means that machine is no longer serving your request. So you know that that node is down, that node should be considered down, and then you should have those fallback mechanisms for this node. uh, the other thing which you could do is that, like on an operating system, let's say you have multiple processes running, multiple processes hosted, right? So you could have some script or some monitor running at your OS level, and as soon as it detects that one of the processes crashed, then it kind of send messages to other nodes that this process has crashed on this machine, so that you know that your your this node is down, and then again you can take whatever fallback mechanism you want to do. So these two were the failures that are happening on the processes that are running your machine. The third and fourth are those network, like detecting kind of these networking faults. So one of the thing that was mentioned is that if you have access to the management interface of your network switches, then you can make a query to those network switches, and it could tell you whether it is working or not, whether it has failed. Uh, but this option you need that management interface access to your network switches, and which is not possible over internet, right? Because over internet you don't own those network switches that are on the route, so you don't have that kind of access. The other thing is that the your routers, uh, if they if they have been given a request for some IP address and the router for sure knows that this IP address is unreachable, then it can reply with this ICMP destination unreachable, by which you know that your node is down, and then you can again take necessary action against it, right? So these are the situation where you will get where you will know exactly that something has failed, right? uh, but the above situation, but there are some other situations where like none of these cases fall and your system will not reply back with anything. So in these cases your system has replied back with the failure, you know the system has failed. But in a lot of other cases your system will not reply at all, and so you don't know exactly that your request is being processed or it has failed or what, right? You have not got any response back. So as we have discussed, so now in these kind of scenarios which happen more often, the uh, the the remedy that you have is to use timeouts, right? You can use the timeouts in your system, and these timeouts will help you detect whether your service was running like whether you should be waiting for the response anymore, or you should stop hoping to get back a response, and you should do you should take the next steps assuming that the request has failed, right? Okay, so now moving on. Now the thing is, how do you detect this timeout? What should be the value of this timeout? When would you say that your request has failed? So before I move there, is there anything someone wants to end? Someone wants to add, or are there any questions? Okay, so yeah, so how do we detect these timeout, right? So the problem, the weird situation is that if your timeout is too less, right, then you might have falsely detected that a node is not working, because if you would have waited for a little bit more, you could have got the response back, right? And if you have too long timeout, then the problem is, if actually your system was down, if actually your node was faulty, then you will take more time to actually know that your node was faulty, right? So that's why you need a right balance. You should not have a too early timeout, or you should not have a too long timeout, right? So what should be that optimum value? We are going to discuss that, but before that we are going to discuss why it takes too long, right? Why could it take, why your response could actually be successful, but it is stuck somewhere on your network and it is just taking more time, right? So we will understand what are the reasons of delay in your network, which could cause your request to be actually successful, but it is just queued somewhere in this entire process, right? So which is the sections that reasons for delay, right? uh, so uh, so basically when you are sending a request, that request can be queued at multiple stages in your system. So let's see what are the various places where your request can be queued. So the first thing is the network switch itself. Your request could be queued on the network switch. So looking at this diagram, if you see that these are the input ports and these are the output ports, and this is the network switch in between them, right? So now if you see that if most of the ports are sending the request to this port 3, right, which is their destination. So this is the source, this is the destination. Then the router will queue the request because this port has become full, right? This port has become full. So the network switch has its queue and now it is going to queue your request, right? So basically your request is queued over here, and that's why it might be delayed. Your response might be delayed, but it still might be successful. The other thing where your request could be queued is at the OS level. So when your request packet reaches the node, and if your CPU sees, if your CPU core sees, if your all your the CPUs on that machine are busy, then the OS will queue that request, and whenever the CPU core is free, then it will execute those requests, right? So here the request was queued at the OS level. Now imagine the situation where these multiple OS are running as VM on a machine, right? So that OS itself, it could be queued by a VM monitor, right? Because again, for that overall machine, the CPU was busy with that other OS, with operating that other OS. So again, your request could be queued at that VM level, where first when your OS gets its quanta to execute, then the request will reach the OS, and then the OS, inside the OS, it will get executed. And then the fourth scenario is that your request could be queued at the sender level itself. Your sender, you yourself could queue your request. And this happens in the scenario like where TCP will perform a flow control. Like TCP will apply a back pressure, and TCP will let you know that those nodes are already busy, so you cannot send multiple requests at the same time. So then your application itself will be like putting your request in the queue, right? So these are the various places we have seen where the request could be queued. Uh, the thing about this queue is that so the problem with these queues is that you don't know how long will it take for this queue to be to your for your request to actually get executed, and how long you should wait, right? So this is called unbounded delay. Like you that maximum amount of time after which you can surely say that your request has failed, there is no upper bound on it, right? There is no upper bound. It could be anything, right? So uh so that's uh, so that is something that we have to take in account. Yeah, and the other thing which was mentioned is that so the TCP packets, when they are sent, TCP, so when TCP is sending the request, uh, if it does not get response from the destination, it will itself retry and send that packet again. So although the sender is not doing a retry, the TCP itself is doing a retry, but it will, like, if it sees that it has not got the response, it will again retry. So that is also causing some amount of delay, because your packet was your packet failed, it was retried, but you as a client, you are seeing that you are still waiting for the response, and behind the scenes this TCP is doing this retry, right? So now, discussing about this TCP, there was this interesting discussion about the difference between TCP and UDP. What are the situations in which we will use TCP, and what are the situations in which we will use UDP? uh, so TCP as a way of communication is a more reliable network communication, and the advantage is that it will retransmit any packet which has lost, right? uh, Whereas UDP does not retransmit, and it will not perform flow control. So the thing is with UDP, like either your packet will be sent or it will fail, like it will not do a retry. Whereas with TCP, like it will again and again retry to send the message. So what are the situations in which you like we would prefer to use TCP versus UDP? Is uh, like when you're making a phone call, right? When you're making this video communication call, so then in those situations, like it does not make sense that you retry and send your message. If your video is running, you send your video after a delay, right? Instead instead what you could do so n- instead what you could do is that you could break, like you could I think the example was not video, it was audio. Yeah. So imagine you're doing a audio call. So for that moment, you could freeze. Yeah. Or in the case of scenario in the video also, you could freeze. The application could handle in such a way that it's freezing the video, or it has brought the silence in the audio call, right? And then the receiver, it will ask itself that, hey, you should that there was a disconnection and you should repeat yourself. So here the receiver is manually asking the sender to retry, rather than handing over to TCP, which will retry and send the packet. And why? Because if you are sending this kind of message, which is very time sensitive, if you're sending that in delayed time, then it's of no use. Whereas if you're using your network for sending this email, or browsing web, or sending a file, then even if there is that slight delay, right? Even if there is a slight delay in accessing that web page, it's okay. So that's why those are the situations where we use TCP. Okay, so now coming back to our discussion of what should be the value of those timeouts, right? So the way to so now we have seen that there are various kind of delays that can happen in the network. So the best way to choose the timeout is that you do it experimentally, that you run an experiment where you're sending large number of requests over some period of time on multiple machines, and then you are waiting for the response back from those machines, and you see what is the average latency, what is the average response time, and based on that you are deciding that what should be the right number to consider for the timeout, right? And the other thing is that you don't have to make this number fixed, like this the exact timeout number. You can even make it variable. This experiment of like making multiple requests over some period of time, this could be a continuously running experiment, and based on whatever response times you're seeing, you could make your timeouts as a variable, and depending on the time they could be more or less, right? So like for example, if you see if you're observing this pattern that in some peak busy hours, because of lot of network congestions in the working hours, generally it takes more time for your response, because lot of requests are stuck in those queues. Then during those peak busy hours, you could have those increased timeouts. Whereas in those non-peak hours, you could have a lesser amount of timeout, because the chances of your request going in the queue are lesser, and that's what you would have observed from your experiments, right? So so that was about setting the timeouts in your system. Okay. Then moving on to, so at the very top of this chapter, we have discussed that internet uses asynchronous network, right? So now let's go deeper into this subject, that what is the difference between synchronous and asynchronous network, why the internet is actually made up of asynchronous network, right? And what will happen if we are using synchronous network, right? So basically, this thing is quite interesting in this way that so we have been, so this entire section above, right, we have talked that the network is unreliable, and we have seen how network is unreliable, how we have seen that there are unbounded delays, and we don't know uh, what happened to our request, and whether it actually succeeded, failed, or it got stuck, right? But if we want, if we are given a chance to design a network which is reliable, which has bounded delays, for which we know for sure that the request was actually succeeded or failed in some amount of time, can we do that? So yes, we can do that. Uh, if we use synchronous network, if we don't use asynchronous network, then we can make our system more reliable, and we can have those bounded delays, right? So the example of synchronous network is your telephone, so the landline telephone network that existed before, right, before this voice over internet or cellular network. So in that case, what used to happen was that between a sender and a receiver, when sender is trying to establish a connection, then a fixed amount of bandwidth is allocated over the network for your call. And that bandwidth is reserved during the call. So now, since you have reserved this bandwidth in the entire network for your call, you have avoided these situations where we discussed above, that where the things can get stuck in queue, because now you have reserved that space for your call. So now there will be no queues, and your request will be served in your reserved network space, right? And in those situations, then your network will be more reliable during when your call is established, right? So what is the disadvantage with this situation? Like, why did we move from this approach of synchronous network to asynchronous network? Any ideas? Okay, I just want to check if my system is working fine. I don't hear anyone talking. Is no one actually talking? Or okay, I think, yeah, people are there. Yeah. you guys have to you guys have to add something and talk about something, because anyways we don't have too much content for today. Like, I was thinking of discussing about uh, unreliable network. I was thinking of talking about unreliable clocks next time, because I didn't expect that everyone will be so much silent this time and we could move forward so fast. So yeah, like, yeah, so we have enough time this time, so feel free to jump in, and if you have any questions or if you want to make any comments. So yeah, moving on to this synchronous network over asynchronous. So we discussed this landline connection. It was a synchronous network, and we reserved the fixed amount of bandwidth, right? So so this kind of network had no queue, and it had this bounded delay, right? uh, Whereas if you look at the asynchronous network, this TCP is a asynchronous network in a way that you are sending your packets and you are not first waiting for this overall connection to be established and set and you are getting that reserved space. You are just sending your packets, and then TCP will opportunistically see uh, that whenever there is available bandwidth in the system, it will try to send your packet as quickly as possible, right? So this is kind of this shared architecture where that network is shared among multiple senders and receivers, and we are not allocating that fixed space. So in this kind of network, like we will see these queues and unbounded delays, right? So why did we then actually move to this asynchronous kind of network is all about the reason is cost. So basically, if we have to reserve this network connection among each individual, then now that much bandwidth is wasted, like that much bandwidth is reserved, and now to serve many more customers that you have, like either you need enough space so that you can allocate that fixed space for everyone, or either like I, you would remember that in those days when you would make a phone call, your system will be like in a busy state. It will say that it could not establish any connection because it could not find that empty slot. It could not find that empty bandwidth to make that allocation for you, right? So in those situations, if you have that fixed amount of bandwidth, then either if you have limited space, then many of your customers will be left unserved because you would not have enough space allocation left for them, or like you would have to allocate a lot of space and the system overall will become very expensive to serve your customer, right? So uh, so that's why instead what we're saying is that we will use this queuing kind of mechanism, whereas in which, like, whenever there is an outburst of this traffic, whenever there are large number of requests, they will be put in some queues at multiple places, and as long as the traffic gets reduced, it could be served by overall all that network pipe, then it will be served and it will be responded back, right? So this is what was mentioned, that these data centers, they use asynchronous network because they are optimized for the bursty traffic, right? So imagine that if you have a fixed size of pipe, right, and there is only that fixed amount of traffic that can flow, right? So either you can reserve the space in your pipe for each of the sender receiver, or you could have some queues where whenever there is an outburst, whenever you see that the number of requests are so much that they could not be handled by your network connection, by your pipe, then they will be queued, and as soon as the request goes down, those will be picked from the queue and served appropriately. So in this situation, you are making that maximum optimum utilization of your pipe, of your bandwidth, and you are serving maximum customers as possible. And with this optimum utilization of the network, the cost of your the cost to transfer your data will reduce, right? Because that same wire, that same network is now serving more number of customers, so you can divide the cost among many number of customers because they are being served. That's why, and we have seen this in the real life, the cost of this voice over internet protocol calls and the cost of the cellular calls have decreased much lesser than the previous landline kind of connections, because many more customers are being served simultaneously, so now the cost is divided among many more customers, right? uh, and yeah, and then the other thing which was mentioned uh, is so when you are making this phone call, when you are establishing a connection, like how much bits of audio you are going to transfer per second, so you can allocate that fixed bandwidth space, right? But when on the internet, when you are transferring web pages or when you're transferring email files, each one of them will have a different size, right? Depending on your file size, email size. So basically it's hard for you to guess like how much bandwidth space you need to allocate in your network if you want to establish that synchronous network. And again, if you have allocated the network space which is too less, then you won't be able to send your request. And if you have guessed and allocated the network bandwidth more than it was required by your email or by your file, then you are actually wasting your network bandwidth, because now that network bandwidth could not be used by someone else and you have taken up more bandwidth than it was required. So because of all these reasons, um, this network, this internet uses asynchronous network as a means of communication, right? So okay, so let's move on to latency and resource utilization. So before we move on, can anyone tell the difference between synchronous network and UDP? Like what was the difference? Because in one of the examples we have talked about that in landline kind of communication we are using synchronous network, which is that this reliable network where you get this reserved space. And also we have discussed this scenario of using UDP for phone, for audio video kind of communication, that real time communication, because you don't want to retry and send the messages after some delayed amount of time, because at the delayed, sending that message at delayed time does not make any sense. So what will be the difference between this synchronous and UDP? Like what will be the difference? Yeah, so let's think about these three scenarios where you are using TCP, UDP, or so TCP and UDP are this asynchronous network protocol, whereas the synchronous protocol is another kind of protocol. And what will happen if you are using your phone communication among these three? So according to me, so if you are using this uh, synchronous network for phone communication, right, then the advantages and disadvantages. The advantage is that once your connection is established, then you will see no delays. You will see no you will see no situations where your audio is being dropped or your audio video is breaking, right? And your once your connection is established, it will work very smooth. But the disadvantage is that it's more expensive, right? You have to allocate that fixed bandwidth. Now let's see, in asynchronous network, if you are using TCP to make this audio video communication, then uh, the advantage of using that would be that uh, whatever audio video communication is being sent, if those are considered as packets, whatever those packets are sent, most of those packets will be reliably sent to the destination. None of them will be dropped. But the disadvantage I see is that your packets might be sent at some delayed amount of time. And so basically, like you might hear the sender speaking something after, like after a large amount of delay, right? uh, and yeah, so and I think, like in my experience, I have faced, like I think we have faced these situations, right, where someone will speak something and then on the destination side you will receive that audio or video after that delay, after that long amount of delay. So I think in those situations they are using TCP, where they are trying to send the packets, they are not trying to drop the packets, but then you will see those delays. uh, in UDP, like, you will feel more kind of real time communication, that when the sender is speaking something, you won't see those delays. You will see that your messages are being sent at the real time, but then whenever there is any failure in those packets, they will be just dropped. So your communication will have those lots of breaks and pauses, and it will be breaking, but overall it will feel like more real time, that when the sender is speaking something, it is being received by the receiver, right? Okay, so uh, the next topic is latency and resource utilization. Yeah, so this the things which we have discussed before, where we have said that there is this unbounded delay, this variable amount of delay, that has been caused because we have that fixed amount of resource, and that resource has been dynamically allocated rather than doing the fixed allocation of that resource, right? And the thing with this is that you are increasing your resource utilization by dynamically allocating the resource, but it has caused increase in latencies. So basically, latency and resource utilization are inversely proportional, right? if if you want to optimize your resource utilization, you will have to make some queues so that those outbursts could be stored in the queue, right? And so, but you will see like increase in the latencies. Whereas if you want to have low latencies in the system, right, then you will avoid having those queues. Like, you will either say the request has succeeded or failed, right? And you will, so so in that case you are not making a best use of your resources, because during that outburst, when that outburst happened, rather than storing the messages in queue or something, you just failed most of the messages. Only the messages which could have been served by the resources available, you are just serving those messages. You are failing most of them. And now, just after that outburst finished, now your resources could have been utilized and could have served your request, but you have already responded failure to those requests, and now the it's the responsibility of client to retry, right? So basically, in this situation, you are not making the best use of your resources, right? So so that's what we're saying here, that like, if you don't allocate fixed resource, if you doing the dynamic allocation, then the sender sends the packet, and the network switch decides that how to queue those packets and which packets to actually send, right? So this has this advantage of queuing, but the advantage is you are making this maximum utilization over the wire, right? And the wire has fixed cost, so you are making better optimization of each byte that you're sending over the network, right? This similar thing is also seen in like CPU core when multiple threads are running, right? So uh, so like, when multiple threads are running on this system, then CPU code does exactly same, that it will queue your request, and it will, so those, some of the threads will be paused, and the ones which could be served, which could be run by the CPU core, it will be run. And when that thread is like waiting on some input output, then the CPU will quickly switch and start start making those CPU cycles, and uh, making those computation on another thread, which could be, which has the potential to be served right now, right? And similar, this similar kind of queue mechanism like this, uh, this is seen like across this distributed system, that basically if you are designing a system, let's say if you're designing a system which is a messaging system, right, where the sender sends the message and the receiver receives the message, then basically you will use a queue, right? And the advantage of having the queue is that if the receiver has those outbursts of message, or if the network is busy, rather than dropping that message, rather than dropping it, it will be stored in the queue, and whenever the receiver has appropriate bandwidth, whenever the receiver has appropriate resources, it can pick the message from the queue and it can process it, right? So yeah, so this yeah, I think this was overall about unreliable network, and how, like, what are the things we can do to make the network reliable, but again then it increases the cost. So uh, so one another thing I was thinking is that like, so we have seen that this synchronous network, it has these advantages, and like the telephone network used to use this synchronous network, right? So are there any real life examples that we would be using synchronous network for? We said that internet for most part uses asynchronous network. So what would be the situations where we will be using synchronous network, where we want more reliable network communication? And again, like, you have, like, in those situations, it's okay for you to pay that extra cost, right? So like, one of the things I was thinking is like this airplane controlled traffic, right? If it is using its network communication, then it has to be highly reliable, right? And it's okay to pay the extra money, extra cost, but it's not okay that your network is unreliable, right? So I'm assuming in those situations, like, they would be probably kind of using synchronous network, where, yeah, where you have that, you have invested more amount of money to allocate the bandwidth, so that your network communication could be served by this network, and it is synchronous and more reliable, because you cannot, if your important kind of communication is stuck in the queue and it's not delivered on time, then it can create like big problems for you, right? So yeah. Okay, I think this was pretty much it regarding the unreliable network. I don't have unreliable clock fully read through. If someone has, they can start, and they can probably discuss about it, or if we want, we can discuss more about it, or else I think we are done for today. I don't have anything else to add. Okay, so I think I'll stop recording. At least I'll stop recording because uh, we are done with this part of this chapter. Then we can discuss more.